Hello and welcome, everybody. We're really happy to have you all here. My name is Bert Pablo. I'm the staff astronomer at the AAVSO. On the panel with me, I have Stella Kafka, our director, Bill Stein, a board member and AAVSO Net's member and enthusiast, and our BSM section leader, Dave Cowal. I'm glad that you all are here so that we can enjoy this fun topic today. Today, Dave is going to tell us a little bit more about the BSM section and what it has to offer. So the overall schedule you can see on the screen. We're going to talk, or he's going to talk a little bit about the story of Henrietta Leavitt, give you really an idea of what BSM is. It's the Bright Star Monitor, but what does that mean? Where are the telescopes, everything like that. Its mission, more about it. And then he's also going to talk about the different educational opportunities that are available to you, as well as we'll have a rather long Q&A at the end so that you can ask any questions that you might want. At this time, I am going to introduce Dave, let him have control of the window so that he can open his new, so that he can open his presentation. Just one brief thing before we start. I am going to disable chat so that it's just to the panelists for now, so that we can keep up with questions from everybody and see what's going on. And if you have any questions, you can ask them under the Q&A section or in the chat. If they're technical in nature, we'll try to answer them as soon as possible. If not, then we will collect them, and once the Q&A starts, we will start answering those questions. Then if things require more detailed answers or someone needs to speak for any reason, we can address that at the end. Okay, without further ado, Dave.
Welcome and good afternoon, everybody. We're delighted to start our webinar series discussing the Bright Star Monitor remote and robotic telescope network. I think all astronomers, whether they are amateurs or professionals, all suffer from a highly contagious and incurable disease, which is known as aperture fever. And that means you want bigger and bigger aperture telescopes so we can look deeper and deeper into space, looking at the origins of space and time. But when we do that, we neglect the near sky. And so the whole idea of the Bright Star monitors is to use smaller telescopes so that we don't saturate our detectors with these large aperture instruments. And we get a sense of what's going on in the stars closer to the Earth. And there's a lot of science to be done here. There's a lot of variable star science to be done here that can be applied to all of astronomy. So this is an important area and a somewhat different take, I think, on a telescope network. The network is not perfect. Just like anything made of parts breaks down from time to time. We are never going to get it perfect, but we're always going to try to get it better and try to make it more useful to those that use the system and to the scientific community in general. If you have already went to our website and did some reading about the Bright Star monitors, I will say to you that the website is woefully out of date. We are well aware of that. We're in the midst of a rewrite not just for the Bright Star monitors, but for the whole website. So we will try to make that much more reflective of what's going on now in the not too distant future. So please bear with us. This is also a very diverse audience. And so I hope we have a little something here for everyone. So my agenda for the first hour is going to be a formal presentation. And then I'm going to defer to my partner, Bill Stein, who knows a whole lot more about astronomy than I do, to answer your questions. First, I want to talk about the story of Henrietta Leavitt, because I think it gives you a nice introduction to what variable stars are and to the AAVSO. Talk a little bit about the history of the Bright Star monitors, what its missions are, the various hardware that we use, the software we use, and how all that integrates together. Talk to you a little bit about our latest entry into the Bright Star monitors, the Emily Morgan telescope, and particular interest to me because this has kind of been my project. And then hopefully the second hour between 3 and 4 today, we can address your questions. So I was going to tell you a little bit about the Cepheid variables, but I found this very short video that I found did a better job than I could. So I thought we'll start with this.
Had a big problem. When they looked up into the night sky, they couldn't tell how far away most of the stars were. As a matter of fact, before 1912, we could only accurately measure distance within a few hundred light years. Nobody knew how large the Milky Way was, or if stars outside the galaxy even existed at all. All of this changed when a researcher named Henrietta Leavitt made one of the most important discoveries in the history of astronomy. Leavitt's discovery was based on a small, relatively unknown group of stars known as Cepheid variables. These stars are called variables because their brightness changes over time, and Cepheids because the first one discovered was in the constellation Cepheus. Change in brightness can occur in variable stars for all sorts of reasons, but the changes in Cepheids occur due to helium in the star's atmosphere. When the helium is heated, it becomes more opaque, making the Cepheid dimmer, and when it cools, it becomes transparent, making the Cepheid brighter. The change in brightness of a Cepheid over time can be plotted on what is known as a light curve. The amount of time it takes for a Cepheid variable to pass through one full cycle on the light curve is called the period. The periods of Cepheids have a unique trait that separates them from other variables, which is what Henrietta Leavitt discovered back in 1912. At the time, Leavitt was studying Cepheids located in the small Magellanic Cloud, a nearby dwarf galaxy. She noticed that there seemed to be a direct relationship between the period of a Cepheid and its brightness. The Cepheids with the longest periods had the highest average brightness, while those with very short periods were generally quite dim. This revelation was incredibly important to astronomy. Why? Well, for the first time, we could determine a star's true brightness. When looking at normal stars, it was impossible to tell if one that appeared bright was actually bright or just close to us. But with a Cepheid, we could find its true brightness using its period. Then we could compare its true brightness to its observed brightness to find out its distance. For example, if the Cepheid has a long period but appears very dim from Earth, then it must be very far away since a long period implies a bright star. The most important impact of Cepheid stars, however, has to do with the stars and galaxies around them. When the distance to a Cepheid is found, it can be used as a celestial distance marker, telling us information about how far away the stars around it are. Suddenly, astronomers had a way to find accurate distances to anything remotely close to a Cepheid. This expanded our range of distance measurements from a few hundred light years to a nearly limitless range. All of this new information told us all sorts of things we had never known about distant stars and galaxies. For example, in 1924, Edwin Hubble used Leavitt's period brightness correlation to measure the distance to Cepheids in what he called the Andromeda Nebula, and discovered that it was not a nebula, but one of many distinct, separate galaxies. This was one of the most important discoveries in modern astronomy, proving that the Milky Way was not alone and demonstrating just how enormous our universe is. Almost everything we know about astronomy today, from the Big Bang to the existence of black holes, we know because of Cepheid variables. They are perhaps the most important type of star in the entire universe. A long time ago,
Well, hopefully that gives you a little background about some of the importance of variable stars. And Miss Levitt published her article about the period luminosity relationship that you heard discussed in the video in 1912. The year before, the American Association of Variable Star Observers was formed. It was initially part of the Harvard Observatory, and it has subsequently become an independent nonprofit organization. Today, we have around 1,300 members all over the world, a wonderful association between amateurs and professionals who are doing good science and having a good time while we do it. And in this initial picture, you can see Miss Levitt front row center. Do have to comment that at the time that the AAVSO was formed, women were not allowed to be astronomers. They were considered human computers, and they were used to do the mathematics, but the male astronomers got credit for the work. Miss Levitt was the first author on this extremely important publication, and it wasn't until after Hubble determined the distance to the Andromeda galaxy that the real significance was appreciated, and there was some effort to nominate Miss Levitt for a Nobel Prize, which she certainly deserved. But unfortunately, she had an advanced cancer and passed away before the nomination could go forward. And as you may know, the Nobel Committee requires you to be alive to receive the Nobel Prize. Times have certainly changed, but I think it's important to understand the history as well. So with that as a little background to the AAVSO, I wanted to talk a little bit about the Bright Star monitors and how they got started. Our board used to be called the Council, and a discussion in the fall of 2008, it was decided to create a Bright Star monitor to look at Epsilon Aurigae, and the council members themselves funded this project. We'll talk in a minute a little bit about that particular star, but actually all of you have probably looked at it from time to time. It's very close, as you can see in the little image to the right, to Capella, which is a bright navigational star. If you look to the south on a clear winter evening, it's one of the prominent stars in the sky, and it's within your visual field of view, looking at that star. So in 2009, the AAVSO got a NSF grant to study this star, and we installed the Bright Star monitor in Cloudcroft, New Mexico in April of 2009. And you can see at the top of your screen a picture of what this original Bright Star monitor looked like. The instrument was a 60mm refractor, which means a lens telescope. The mount was a inexpensive computerized German equatorial mount, and a sort of basic CCD camera to image the star fields. So why Epsilon Aurigae? Well, this is a different type of star than the Cepheids. This is an eclipsing binary star. So here we have at least a two-star system, and the stars are orbiting around the center of mass. And if the geometry is right, such that our field of view from Earth puts the orbital plane somewhat close to our angle of viewing it, then from time to time, one of the stars is going to get in front of the other and eclipse it. Well, this star is very unusual, and you can see at the bottom of the page here, its light curve. This is a little more confusing than the light curve you may have seen when we looked at the Cepheids. and that there are multiple curves here, and each one represents a light curve with a different photometric filter put in the light path. And these photometric filters are basically designed to allow only a narrow band of photon energies to go through the filter. So we can actually measure the brightness of the star with various energy photons, obviously within the visual range. Higher energy photons are generally filtered out by the Earth's atmosphere, and you got to put a telescope in orbit to get above the atmosphere to measure those higher energies. But this star had a period of approximately 27 years, and when the star eclipsed its other star, we got a very strange flat bottom curve. The bottom of the curve is about a year, and each of these two shoulders is about another 6 months. So we really didn't understand what was going on here. So I told you in the spring of 2009, we got this grant. The star started to fade as the eclipse began in August of 2009, and our Bright Star Monitor started to observe the star in September of 2009. In the graph on the right, you see a blow up of kind of the flat bottom of this curve, and every one of these big blue plus signs represents an observation done by the Bright Star Monitor. So we contributed a considerable amount to our understanding of what's going on with the star, or the star system basically. It's really not understood fully even to this day, but the leading theory is that the dimmer of the two stars has an accretion disk around it full of dark dust. And so we're seeing not just the one star eclipsing the other, but actually this dust cloud as well. So building on this experience, again, with the network starting small with one instrument and one project, the project grew. We put in other Bright Star monitors in various locations. We learned some things with a little experience. We learned, for example, that the mounts we were using were fine to be used on occasion by observers, but for the intense observations all night for every clear night, they weren't durable enough. They were breaking down, and we needed more durable mounts. We also discovered that our 60mm refractors were just a little bit too small because we were having scintillation effects, and a little bit bigger instrument would help. So we've gotten a lot of donations. We've got a lot of equipment donated in kind or given to us on long-term loan in kind. And the system has grown and upgraded considerably. The key is our instrument in New Hampshire. And this is basically where all new equipment is tested, and before we send it out throughout the system, we've hopefully ironed out most of the bugs. And when a problem erodes, which usually means some sort of a software glitch, one of these bloody Windows 10 upgrades that tend to cause havoc with the system, we get the problem fixed in New Hampshire, and then once we know what's going on, we can spread it out to the other instruments. So we have an instrument currently also in New Mexico that Bill Stein manages that location. We have one in Hawaii. We have ones on the east and west coasts of Australia. Interesting about Australia is the weather is such that when one coast of Australia is clouded over, the other coast tends to be clear. So we usually one of these two sites is going to be functional pretty much every night. The Texas project has just come online this spring, and we'll talk about that later in my presentation. And we have a possibility of one additional site in Argentina. Currently, the pandemic issues have kind of put all that on hold, but we are hopeful that that location develops as well. So the goals of the network are to show that we can do precision photometry with small telescopes, and the photometry can be done from bright urban environments worldwide. Now, the picture you see here is our headquarters in Cambridge, Massachusetts. And to try to prove that point, we actually, for a while, had one of the Bright Star monitors on the roof. So this is Cambridge, this is Boston area, lousy weather, a lot of snow in the wintertime, a lot of cloudy nights, a lot of light pollution from Boston. And I still had some good data that came from the rooftop of headquarters. We wanted to show that we could maintain a low-cost, remote, robust robotics system. It can be used to calibrate comparison stars for bright targets. We can get often the first bright star light curves in multiple filters. It's a good opportunity to test equipment for robotic observing. I think it's been a good school that people who want to obtain their own equipment for variable star observing can kind of go to school on what the experience of the Bright Star monitors have been. And it's a membership, and it's a benefit that we've offered to the membership. So there are 3 missions currently of the Bright Star monitors. The first is proposals, so that requests for usage and the projects get set up and run. The second is the Bright Star survey. And our newest mission is to develop educational projects. And we'll talk a little bit separately about each one of these. The proposals are open to any AAVSO member. If you're not a member and you'd like to use the Bright Star Monitor Network, it's very inexpensive to join. We would love to have you as a member. We'd love to have you using the BSMs. Entering a proposal is very easy. You can see the proposal form in the lower right of your screen, which is on our website. It's you write a simple paragraph and you list the target stars. It doesn't have to be an extremely complex proposal. We want to approve your proposals. The main reason we reject proposals is because they're duplicates. It does have to have something meaningful in it, but that could be certainly be an educational project for a college astronomy class would be perfect. If it's something that you are hopeful that you can eventually publish, that's wonderful. We'd love to have publications that involve the AAVSO. We do have a large database, the AID, and at a minimum, any measurements that you've taken, we'd like to have them entered into our database. So perhaps in the future, someone else could make use of those as well. So the proposal goes to the Telescope Allocation Committee, and they make a recommendation. If approved, the observing project is automated. We can specify constraints to that, or you can as well. We certainly will work with you. My experience has been sometimes the original exposure lengths for what have you are a little short or a little too long. And so that we often have to make some adjustments, but once we get it figured out, it tends to run very well. The images are calibrated and then sent to either the FTP site or VFOT, and I'll talk a little bit more about VFOT in a couple of minutes. So those are available for you to use and evaluate. We send you an email notification when images are in your account. And we provide a forum where you can comment, make suggestions, ask questions. So I wanted to give you a couple examples that I have used. I submitted a proposal, I think in 2012 or 2013, to study CY aquarii. And we used instruments from the roof of headquarters, New Mexico and Australia at that time. I was able to get 21 new maxima and did some analysis of the period of this star. Peculiarly, this star has had a period that has shortened and lengthened almost in a sinusoidal pattern over a long period of time. We also noticed that based on the spectrum of this star, it looks like it's very, very old, and the star should no longer be shining. Its nuclear furnace should have long ago run out, and the star should have become a white dwarf, basically a cinder gradually dimming throughout all eternity. But in fact, the star is still pulsating and still very much alive. It's been speculated that this is because the star was actually fused from two very ancient white dwarfs, but we really don't know for sure. So here's some of my data. Here's a light curve from one cycle using 4 different filters. And I think you can see that very nice photometry from the network. The error bars are very small. And I tried to calculate a model for the period of the star. And so what you do is you put one light curve cycle on top of another, and you build up a much larger model of the light curve called a phase plot. And then using some computer wizardry, tried to calculate a mathematical model that would best predict this phase plot. And this is basically a hairy trig function. You can see it's not perfect. The time of maximum, the model doesn't quite get it right, but it comes pretty close. And then if we do a residuals, where we take each observed data point and we compare it to what the model says it should have been, so we subtract the calculated from the observed and we plot that as a residuals, I get pretty close to a straight line, which says that the model is actually pretty reasonable. So an example of one project that an amateur like me could do. And this is also an opportunity to mention the journal of the AAVSO, which is our own open access publication. It is a peer-reviewed journal, but it is very receptive to manuscripts from young investigators and from amateurs. And I found the referees were very willing to work with me and help me get this together in a format that was appropriate to be published. The second project I did through the network involved a very different kind of star, BW Vulpeculae. And this is a beast of a star. It's about 15 times the mass of our sun. And it is probably just about running out of its hydrogen fuel in its core. It is a rapidly pulsating star. And the star, about every 10 to 15 years, has had a gradual increase in its period. And peculiarly, it has been overdue for one of these period changes. So I did a project in conjunction with a professional astronomer, and data from the Lowell Observatory in Flagstaff. And so if you plot the observed minus calculated, the O minus C numbers for this star, and the negative, the signs here demonstrate a historical data. And you can see for the last 20 years, there's a good linear fit to this data. And a straight line suggests the period is staying the same. And then beginning about 2009, we started to see a new line form with a very different, more negative slope compared to the historical slope. So this negative slope suggests not a period increase, but a period decrease. And this occurred later than expected and occurred in the wrong direction. We don't know quite what to make of this. Speculation it is due to convective effects within the star, but nobody really knows for sure. And this was nice experience as well, in that we could compare the data from a professional observatory, the Lowell Observatory, and our data from the Bright Star Monitor Network. And we found they were very congruent. In fact, there were a couple of occasions where we actually observed the same moment using two instruments, and the data was almost superimposable. So feel very good about the quality of the Bright Star Monitor data. So just from personal experience, those are good examples of the kinds of things that amateurs can do. So since the network started, I plotted the number of proposals per year. It initially went up and then we declined for a few years. And this is when we were starting to have problems with the equipment not being robust enough. And with the new equipment coming online, proposals have steadily gone up. We have had a lot of publications, and that's certainly a good indicator of professionalism. But again, you don't have to feel I can't submit a proposal to the network because I don't feel sophisticated enough to publish. We certainly accept a lot of proposals where there is not going to be a publication. So currently the proposals represent about half of every night's work for the network. The other half comes from the Bright Star survey. And this is a survey that has a priority set below any of the proposals. It almost perfectly keeps the telescope's imaging throughout the night. And it represents approximately 2,000 underobserved bright variable stars. And over 10 years, we've observed pretty much all of these stars about a dozen times each. So the idea here is that if the number of proposals go up over time, then more and more of the night's observations will be done through the proposals, and the surveys will become a lesser number. So there's plenty of space to expand in proposals. Now, I've been talking about the missions of the Bright Star Monitor, and you may be wondering who this guy is. And when I was a little boy, my favorite cartoon character was Marvin the Martian. I don't know if any of you are particular fans of him, but Marvin had a mission also. And his mission was to blow up the Earth. Fortunate for us, that didn't happen because Bugs Bunny always outsmarted him. But his big problem was that the Earth always got in the way of his viewing Venus. So that was my first inkling that I thought astronomy was cool, was thinking about Marvin the Martian. So let's talk a little bit about the hardware that we use. And 5 of our instruments, excuse me, all have the same pretty much hardware. And this is a picture that Bill Stein sent me of the New Mexico instrument. You can see it's a little bit more complex than what the original Bright Star monitor looked like. It has a very robust ME mount, which you can see in red. The telescope is a 180 milligram f2.8 astrograph. So instead of being a refractor, this is a reflector or mirror telescope, although it does use some corrector plates. I believe this is the only commercially available telescope that is in bright canary yellow. So there's never any doubt what, if you see one of these, what it is. The sensor in the camera, and the sensors are basically photon counters, a lot more complicated physics than that. But instead of what was in the original instruments, this one uses CMOS technology instead of the CCD technology. And if you think you don't know what that is, if you have a cell phone, the camera in your cell phone pretty much uses this technology as well. It is tuned to give resolution of 2 arc seconds. And if you're not familiar with how telescopes work, magnification really isn't all that big an issue. We can magnify anything as much as we want. The real question is how much resolution? How detailed can we get? How close together can 2 points be? And the instrument can recognize them as 2 separate points, which in our case would be 2 separate stars. And these instruments will yield a field of view of 1.8 degrees. And having a big field of view is important because it means we have an opportunity to have a lot of comparison stars in the same field of view. So the real question is, how does all this come together? Seems like a busy slide, but this really, I think, is very intuitive to me to help me understand how all this works together. So basically, there are 3 pieces of hardware. We have the mount, which you see here, and the mount's job is to slew the optical tube to a particular target that we're interested in, and then to track that target across the sky. We have the optical tube, whose job is to collect the photons of starlight and focus them. And then we have the camera, and its job is to image these stars and basically count the number of photons in the stars. And controlling each one of these pieces of hardware is a dedicated software program. We have a navigation software program that controls the mount. We have an imaging software program that controls the camera. And then we have a focusing software program that controls the optical tube. And what's really cool about this is that we have an executive software program that controls all the other software programs. Now, my name is Dave, and I've been a big fan of 2001: A Space Odyssey. And so I can't help but call the executive software program HAL, but that's just me. So, and this is a snapshot of the computer screen during a typical night's run, and you can see windows popping up for all the various programs that are running and controlling each other. So how this works is, if we look at a typical night's observing, in the evening, just as the sun is setting, the executive software turns everything on. It tells the mount to point the telescope straight up, and it starts taking imaging, measuring the brightness of the sky. And when it's satisfied that we're sufficiently into twilight, it starts taking calibration frames. And then when it's got to the point that it determines that the sky is dark enough to start observing, it starts its observing run for the night. And then when it thinks it's getting close to morning twilight, it again points the camera up, starts taking more calibration frames, And when the sky is too bright to take calibration frames anymore, it takes additional calibration frames that don't require getting light from the morning dawn. It applies all these calibration frames to the raw images taken during the night and creates science images, sends those to where they need to go, and then it shuts everything down. And so how does it know what it's going to image? Well, it has some artificial intelligence here. It has a list of all the potential targets. It knows what the priority that we've given for each of these targets. It knows how well positioned these targets are going to be in the night sky for this particular night, knows where the moon is and if it's going to get in the way, and this and a lot of other bits of information. It grinds that through its brain, and it decides what it thinks is the best image. It does an observing run on that best image, and then it starts all over again. And so you never know for sure exactly what you're going to get in a night's observation, but you can be guaranteed over time that within the network and within the various instruments, you're going to get hopefully the data that you need. So that's how the whole system works. And it really depends upon a lot of people who are a whole lot smarter than I am, some of whom know hardware very well, some of whom know software very well, and engineering very well. And everybody works together to make this, as volunteers, to make this an effective system. So earlier I mentioned vPhote, and most people choose to get their images sent to vPhote, and this is a software program within the AAVSO website for use by members. And here's an example of one image taken by the Texas instrument. For those of you used to looking at these kind of images, I think the first thing that strikes you is just how big the image is, and the fact that we're able to get lots and lots of comparison stars in the image. So the targets here show up as green bullseyes. The comparison stars show up as surrounded by blue bullseyes. And then we have one that is orange, and that is called a check star. So the way this software works is it takes the target star and it compares it to all these comparison stars who we know what their brightness or magnitude is. It looks at the sky brightness and it subtracts that as well. And it computes a magnitude and an error for this individual observation. And it also compares it to this check star, which is basically another comparison star. And we know what its magnitude should be. But it uses this as a quality control device. And vPhote as well can use images from different filters and combine them and do transformation calculations so we can get first-rate quality 2020 variable star measurements. So I want to spend a little bit of time talking about Bright Star Monitor Texas. I want to talk a little bit about not just the telescope, but also the area that it's located in, because I truly believe if part of our future with the network is education, this is a wonderful spot for on-site student projects, or at least for part of their projects, to actually physically see the place. Clearly with the pandemic now, this is not a great time to start traveling around, but that's not going to last forever. So the instrument is located in West Texas. And West Texas is usually considered to be the space between the Rio Grande River and the Pecos River. And the area is just to the northwest of where you see Fort Davis here in red. And on the left-hand side of the screen, you see a light pollution map of this area. And here's El Paso, and across the border is Juarez. And so this is the light pollution from El Paso, Juarez. And up here you see more light pollution from the Midland, Odessa area. But when you get up to the north of Fort Davis, it is literally dark as the inside of a cow here. It was on top of the mountain where BSM Texas is located. The moon was down. It was an overcast night, so there was no starlight. And literally, I could hold my hand up in front of my face, and I would wiggle my fingers, and I couldn't see my fingers. So, I mean, it is the darkest skies in North America. So a great location for a telescope. When you drive from El Paso with a rental car and you turn off the interstate, first time I went out there was in early spring. And as you get into the foothills of the mountains, the view is just breathtaking. You can see the cacti are in bloom and the bluebonnets are everywhere. It is just a gorgeous physical area. About a half-hour drive north of our observatory is the McDonald Observatory, and they have wonderful programs, both daytime and nighttime for students, and so it's easily accessible from the Fort Davis area. Likewise, about a half-hour drive to the south of Fort Davis is Marfa, and a wonderful art museum called the Chinote Foundation, which is unlike anything I've ever seen before. This is not two-dimensional paintings. This is not sculpture. This is just massive installation art. Some of it is outdoors, as you see here. Some of it is indoors. It was the brainchild of a New York artist by the name of Judd, and he brought in a couple other artists. And there are two foci of interest to this art museum. One is space and the other is light. And I can't think of a more appropriate art museum for students interested in astronomy to visit. It literally takes your breath away. So with that as an introduction to the area, kind of right between those two locations is the Dark Sky Observatory. This is on a mountaintop at about 2,000 meters elevation. There are two sort of condominium observatories that are roll-off roof sheds. Each one houses 11 instruments. And here you can see our Bright Star Monitor instrument. And here's a close-up of the instrument. You got to have a little fun in all this, and so I decided, you know, this telescope needed a name, and so we're in Texas, and so I named it the Emily Morgan. Emily Morgan may or may not have actually existed, but in Texas lore, she is a hero, right up there with Davy Crockett. And as the story goes, just before the Texan Army under Sam Houston attacked Santa Ana, which he wisely did during siesta in the afternoon, and the Mexicans weren't expecting it. As the story goes, Emily Morgan was actually in Santa Ana's tent and, shall we say, had him occupied so that he both literally and figuratively was caught with his pants down when the Texans invaded and attacked. You probably know her better by her other name, and here's a statue of her in Houston at the approximate site of what San Jacinto was, and she's holding a yellow rose in her hand, and there's a garden of yellow roses around her. So she is made famous in song as the Yellow Rose of Texas. So the Emily Morgan telescope is a little different from the other 5. It is a 100mm refractor, so it is a lens telescope. It also, instead of a CMOS sensor, it uses a CCD, but a fairly large one. And it has, and even though it's a smaller aperture than the astrographs, this is 100mm, and if you recall, the astrographs were 180mm apertures. We're still able, with these dark sky locations, to get a 2 arcsecond resolution. And actually, the field of view is considerably larger at 2.4 degrees. So in addition to general use, as we talked about with proposals and the Bright Star survey, this is going to be an opportunity for us to use this for our newest use for the network, which is going to be for educational projects. And we're starting small here. One of the things that AAVSO offers are what are called choice courses. And these are 4-week online courses to cover various subjects in astronomy and particularly variable star astronomy. And 2 of these courses deal with basic photometry, parts 1 and part 2. And typically we have had students use their own equipment to do the homework for these courses. But these 2 courses about photometry really lend themselves to people who don't yet have their own equipment, or maybe don't want to use their own equipment at all, don't want to be able to purchase and use their own equipment at all, but still want to understand more about photometry. So the idea is that we can use the Emily Morgan telescope for the homework exercises, and so they can request the data, get and analyze the data, do the homework, and have the same experience than they would as if they were using their own equipment. So this is going to be starting next year for the photometry 2 courses, and the instructors are very interested and enthusiastic, and we're hopeful this will be a first step to many new educational projects. So one of the striking things about this network is just how many people have been involved and how many people have donated their time and their expertise over the last 10 or so years. Here's a list. I am sure that it is not complete. I'm sure there's some people we missed, and I am sorry about that. But I tried to recognize as many people as I could, and particularly recognize Arnie Hendon, who's the previous director, and this whole project was really his brainchild and started when he was the director. So I want to stop here and move on to questions. I showed you the picture of the original Bright Star monitor, but what I didn't show you was the enclosure, and that I wanted to close with. I was never physically present to look at this thing. It obviously worked well, but as an enclosure, it sort of looks like, I couldn't decide if it looked like a Rube Goldberg machine or perhaps something that belongs in an art museum in the Chinote Foundation, but it's certainly an interesting structure. If there's questions that you feel are not, won't be able to cover during this webinar, I've given you my email address and my cohort in crime, Bill Stein's, and so we'd be glad to talk to you. Bill has been busily collating your questions while I've been talking, and so I'd like to stop here and turn it over to Bill and let him answer your questions. And Bill, you need to unmute.
Okay, thank you. Thank you, Dave. And we have a few questions. I won't be able to answer all of them without doing a little bit of research, but I will go through a list that I have here on the Q&A. And the first question asks, how can radio telescopes help in seeing these bright stars? So I guess, we're looking at the variability of these bright stars primarily, and the radio telescopes, they could be used, I guess, to examine variability, but I think it would be quite a difficult situation. I don't know if, Bert, you have any comments on the use of radio telescopes for bright stars?
So there are a lot of uses for radio observations. I don't know specifically what you're asking. As far as I know, there aren't any amateur radio telescopes. Are there? Stella, do you have some information on that? Because I honestly just don't.
Hi, everyone. Actually, yes, there are lots of amateur telescopes. Amateur telescopes from really bright stars come usually from synchronous emission. It's radio flares. So if a star is really active, you should be able to see variability on timescales of whatever is flaring on the star. I do not have, depending on the star, you will have different timescales and you have different signal. So what I would recommend is to just try it. If you would like to submit a proposal on the BSM network, we can monitor the star of your interest, and then you can actually know when data is being acquired. At the same time, you can actually try some radio observations that would allow you to make perhaps a correlation. That's what I would say there.
And again, you have to remember what frequencies are we looking at? We're looking way past the microwave infrared.
Mm-hmm.
So we're looking at variability in that area of the star.
Leon had a comment that radio telescopes for amateurs cost anywhere from $5,000 to $30,000.
Leon, yes. It's actually true. I do know that people also build their own. So if you have access to any of those telescopes, I would advise you to try and take some data. I also know that really good sources for radio telescopes, amateur radio telescopes, are pulsars, because they're really constant synchronous sources. But that's beyond the point of this discussion.
The next question I have is, unless there's more comments on the radio telescope. Okay. Next question says, how is the current load on the network or expected load? Is there a queue for observations, or can the current network size handle the incoming proposals? Okay, and then the last part is wondering because of time-specific observation proposals. Let me address the latter one first. And we have had a student working on a project, and so it was very time-specific because the student was doing some other observation, spectroscopic observation. So we were able to load that into our list of targets and to prioritize it, and so we can usually observe the requested target a few times, depending on the frequency per night, and from different bright star monitors too. So the current load, I think, unless someone has a comment, the current load is really kind of low because we have a list of targets requested by the prime operators, but we can always interject or put in a new target and raise the priority so it can be collected. So I don't think there's a problem right now anyway, because we don't have a lot of requests coming in from observers to observe particular target stars. So once the list of targets goes up, then the load could be a problem. But currently, we don't have a problem, and network size can handle the incoming proposals. Any other comments on this from Dave?
Yeah, I would comment that, the way it's set up currently, about 50% of the observing time is from proposals, and about 50% of this observing time is from the survey. But the survey is set for a low priority, so that you could argue our proposals are only running at 50% capacity. And so the survey could go to 0 if we get enough proposals. So I think we've got excess capacity that could certainly handle, quite a number more proposals.
Okay. And any other comments on that question? The next one is about the sensor, which for most of the Bright Star monitors, except for Dave's, are ZWO CMOS. And the question is about the sensor array and pixel size. I'm going to have to send out an answer to that. I'll have to go and research the camera and with the system and get back to you on what the answer should be, unless someone has an answer to that off the top of their head.
Well, I was going to say that I deliberately stayed away from listing various commercial vendors and just kind of gave some general specifications about the instruments. But we could certainly provide to anyone that wants the make and model of the camera, the telescope, the mount, and all those details. And you can get all.
It's not necessarily about the specific camera, just sort of the array size and pixel size, what we can do. And I think the pixel size is around 2 arc-seconds, but that's off the top of my head. I'm going to have to research that. And I'll check on that and get back to the individual who sent that question in. I guess we're recording this, are we, Bert? And maybe we can send, if people are interested in an answer to a question, some specific question someone asked, I can probably put the answers online or something like that too. Okay, the next question is, do the results of one specific observing run of one system communicate with the other systems on the network? And I believe the answer is the way the target lists are set up, we could actually duplicate observations. So we don't have a way of, that I know of anyway, let's say the Bright Star monitor in New Mexico and Texas might collect the same target during the night. So unless we specifically tell Texas not to take the observations, then it could also take the same observation. So you might get duplicate observations or very close to the same time period for a specific target. Do you have any comments on that, Dave?
Well, the other thing, which is pretty obvious, is depending upon the declination of the star, some sites may be too low to observe below the horizon. So obviously it's just put into the queue for the telescopes that have a reasonable chance of observing it.
Yeah, and of course there's also the weather effect, so that New Mexico might be clouded out and Texas could be clear, or vice versa too. Okay, any other comments on that question? Okay, the next question is, looks like you are using ACP for the executive program, and the answer to that question is you are correct. I don't want to say anything more about that unless, Dave, you want to comment?
Well, it's a wonderful system, and Bob Denny has been a great supporter of the AAVSO and the Bright Star Monitor network for some time. So it's, as I say, I call it HAL, but everybody else calls it ACP.
He
is a supporter also of the AAVSO.
There is a follow-up question to that. I don't know if we know the answer or not.
I think Stella can answer that question about ACP contributor to the AAVSO.
I do know they just donated several filters for the Texas instrument.
Okay.
I had an issue with my microphone. So yes, Denny, Bob and Stephanie Denny have been very loyal friends of the AAVSO. That's all I want to tell you. We're really delighted to have them in our corner.
And okay. There's another question on ACP. It said, is it still used based on Virtual Basic, or does it use more modern software such as Python? I'm not sure about Python. I know it uses the Virtual Basic. I don't know if it's been upgraded. Okay, any other one? Anyone else know anything about that?
It's above my pay grade.
Yeah, I don't think it does. But we do have some other stuff that we use on, that I know I use them specifically for looking at the quality of the, not the images, but of the calibration flats, and that uses a Python program. So we do use Python in part of the BrightStar Monitor software. Any other comments or questions on that?
I believe this is related. Molly says that there is a browser-based scheduler as well that makes it easy to use.
Yes, that is correct. Next question about the passbands. Are they BVRI, and why not U? Okay, we don't use U. We use the Johnson Cousins BVRI, and we also have the Sloan passbands. I think they're the SI, the UG, I think, and there's one other SR. So we do have both the Sloan and the BVRI, the Cousins, Johnson Cousins. I don't think we use that because it's really kind of faint and getting to the edge of some of our capabilities.
Yeah, we're looking forward to trying the Sloan U in Texas because the sky is so dark. But unfortunately, with the pandemic, the production has come to a halt, and so there's going to be a long delay before those become available again.
And okay, any other comments on the filters? Next question is, what camera do you use for the astrograph? And I think I alluded to that, a CMOS camera. And I think the manufacturer we mentioned was ZWO. Any other comments on that? And then it says, next question, in general, are CCD or CMOS cameras the best to use these days? Well, I personally have a CCD camera, and I know Dave does too, but we're migrating to CMOS. Why are we doing that? It's because soon there will be no more CCD cameras for astronomical applications being manufactured. I think they're going out of business. So we have to migrate eventually to CMOS. Any other comments on that one? Okay, next question. Besides the choice courses, do you recommend a book to learn about stars in general and variable stars to help us to make better science? Does anyone have a comment on that?
I would suggest John Percy's book, Understanding Variable Stars. Likewise, we have our own textbook on the website, I believe, which is written for advanced high school or non-science major college, I believe. I don't know if Stella has more to say about that. I've read a little bit of it. I thought it read very, very well.
We do have some material on our webpage about introduction of variable stars. So this is something that people would like, if people would like, they can have access to it. And also our CCD manuals are there and available to anyone who needs to get a little bit more in-depth experience. When it comes to CCDs, we also have a CCD school. It's more or less a very detailed recorded a webinar sort of series that you can purchase in terms of chapters or in terms of or as a whole, if you would like to expand your learning a little bit more independently from the choice courses. So I would encourage you to Google AAVSO CCD School and take a look at the outline of that particular product and see whether that will help you with your learning.
All right, I think that's good. And I think there's a book by Bruce Gary that talks about exoplanet observations. That's very good too. I would recommend that book. Any other comments on this? I noticed someone sent a chat to talk about Hellier's book on variable stars too, which is good. Okay, next question. Is there a preference to using current CMOS sensors over CCD sensors for photometry? I think I alluded to this. I use a CCD camera. I prefer that. But as I say, the CCD cameras are going out of business, so we have to migrate to CMOS. So I guess the preference is if you're going to purchase equipment in the future, you probably should look at the CMOS sensors. We've done some studies on the CMOS as far as dark current and things like that. I believe we had people present papers at some of our AAVSO conferences on that. I think I'm trying to think who did that. Ken Menzies, I think, did a paper on CMOS capability. So you might want to look at some of our publications or some of our meeting papers. Any comments from anyone else on that?
I know a number of CMOS observations have been submitted, tens of thousands, I believe, have been submitted to the our international database using CMOS technology. So a number of our members have quite extensive experience with it. I think Arnie Hendon and Gary Walker both have quite a bit of experience using it and are very satisfied with it.
Right, right. Okay, the next question, are there duration recommendations for proposals? Well, we don't want it open-ended generally, but you probably want to be able to observe let's say a variable star that has a known period, at least through 2 or 3 cycles of the period. In particular, I would recommend that because of weather problems you might have. You want to be able to get your observations taken from a variety of our bright star monitors and under different locations, perhaps. But anyway, if you specify at least 3 cycles of the variability of the star, I think you'll be able to get some good observations at a minimum over 3. Any comments from anyone else?
I think for those that like instant gratification, the very short period variables, you get to see the light curve evolve very quickly. Whereas if you're looking at long period variables with a period of a year or so, it's going to take a lot of patience to see the light curve evolve. So for new people observing, I think it catches their attention quicker if they see something happening fairly quickly.
Well, so you're recommending shorter period variable stars instead of some of these red giant stars that have very long period variability.
Exactly. A lot of the Cepheids are binocular targets, and average period is about a week. So just going out for 5 or 10 minutes with a pair of binoculars doesn't take too long to develop a light curve, which is a great project, I think, for high school students.
And the shorter RR Lyra stars are good too, I would say. Okay, any other comments on that? All right, I think this is the last question that we have here. Observation, planning, and priority is the category, and correlative data for students to supplement. So I guess the question is, do we have certain projects going on where we would like students to supplement our observations? Maybe Stella, you might have a comment on that.
You can look in our database in order to see whether there are any more data. And actually at this point, we have both a photometry and a spectroscopy database that would actually, that are both hosting targets. For BSM, we would really recommend standalone projects. You can definitely design your own project, short-term or long-term, as long as it has some beginning and end. That's my only comment.
And I think we do have some sort of a tool, as I recall, that will tell an observer what are stars that require some more observations, of supplemental observations.
Yes, we do have what we call a target tool that is that has stars that are recommended for observations. Some stars do not have many characteristics, so they're really good targets to follow up, and some of them are visible only from the northern and the southern hemisphere. So depending on where your telescope is, or whether you want to ask for a specific BSM telescope, you can select your target. Actually, we have questions about the brightness range of the telescope. So I think this would be a good time to talk about how faint or how bright targets can be reached with BSMs. Bill?
Well, as far as brightness, I think we can go pretty close to second magnitude on the bright star monitors, and down to maybe, with some signal to noise problem, down to 12th magnitude or so. Mm-hmm. I think that's the general magnitude range, with the sweet spot being between 4th and 10th magnitude with the bright star monitors.
Very nice. Also, we have a question whether images are stored on the FTP server can be accessed by default. So the main idea is for those images to be imported on default, correct?
So I didn't quite understand that. The question is, where are the images being stored?
No, whether the images that are stored on the FTP server can be accessed by default directly, or do we have to actually download them on our computers?
My understanding is that they all go to the FTP site under your observer initials. And if in your proposal you request BFOT, it will go to BFOT as well. And that's the easiest way to access them.
Right.
There is a question, actually there are a couple of questions about CCDs versus CMOS. Do you want to comment on that? We do understand that individuals are worried that CCD cameras will become obsolete at some point because manufacturers are not going to make them anymore. Do you have more comments?
Yeah, I think that's the general consensus, is that they're going, the CCD cameras being made for astronomical purposes are going out of business. So you might be able to get your camera worked on or fixed if you still have a CCD camera, but you probably should look at migrating to CMOS. I think that's the general consensus.
So a follow-up question, are the data different using CMOS or CCD cameras?
Okay, say that question again, Stella, I'm sorry.
Are the data different using CMOS or CCD cameras?
I would have to take a look at the observations and compare them. You know, we do store all the observations for particular stars, and we can look at the processed observations to see how they compare from CCD versus CMOS. I don't think we've seen any major discrepancies or differences between magnitudes that were derived from CMOS cameras versus CCD cameras. I think that as long as you do the proper calibration, that is with the darks and the flats, as long as you correct your observations for that, I think you shouldn't see any distinctive differences between the magnitudes you derive.
And calibration data are being applied automatically on the frames before they get to the users, right?
That is being done, I believe, by the people in the AAVSO net. George, I don't know if George Silvis is online here. I didn't see his name earlier, but I believe they're all being calibrated by using darks and the flats.
The question that is on our chat, what is the expected lead time from a proposal submission to the observation window that is to be proposed?
Okay.
Well,
Yeah.
to some extent, it's going to depend upon when the star is going to be, you know, in the right location to be observed. And it also is going to depend on whether there is tweaking that needs to be done with the exposure times or the filters or what have you. But it, you know, if it shouldn't be a protracted period of time by any means. I would expect weeks to months.
Yeah. I'm going back to now some other questions that have come in since we've been talking here, and this probably is something that we should direct to Stella, but what new information do we have on Alpha Orionis, and is it an opportunity for citizen science participation?
Alpha Ori, we have a continuous influx of data. This is a super bright star. This is Betelgeuse, for those who know it with a different name. The new information we have is that it has recovered from its dip and it's doing what it was supposed to be doing. Now it's not available anymore because it's going behind the sun. So that's all I can tell you about this star right now. When it comes to interpretation of the data, Alpha, right now, the dip is considered to be due to dust around the star, some kind of a dust cloud, asymmetric dust emission that absorbed part of the star's light. We don't really know why, though. We don't really know where the dust comes from. From there on, once the star comes back from behind the sun, it is a prime target for anyone to observe. So please keep observing it and we will keep learning about it. That's all I can tell you about Alpha Ori. We also have a very rich number of spectra in our spectroscopic database. So if you're interested in doing a project, an analysis of Alpha Ori data, we have very rich data sets in our databases. So please let us know if you need help to download that data set. We can definitely help.
Yeah, so it is a good opportunity for citizen science participation.
That is correct. Having said that, I think that Alpha Ori is a little bit too bright for the BSM telescopes. So it saturates very easily.
Another question, how will the Gaia and Rubin telescope LSST, Large Sky Survey Telescope, how will these surveys affect or complement your work? Well, the LSST, of course, observes too faint for us, I believe, but we do get some information from Gaia that might see a star that could be variable that we and the Bright Star Monitor Network could look at. But I don't know if we've been getting alerts at all about anything like that. And as far as the LSST, we could be overwhelmed with alerts if we start looking into that. I think, Stella, you may want to comment on that.
Yes, Gaia and LSST are two different missions. Gaia is a mission that is primarily focusing on addressing distances in the universe. So because of that, the data are not very dense. So it can definitely provide information in some stellar variability, but not the detail that one would want for an analysis. So it can complement the BSM's capabilities quite nicely in the sense that you can identify some interesting targets with Gaia and then propose to follow them up and observe them further with BSM. LSST, as Bill observed, is going to be very, very faint. So it won't even affect us in the sense that the saturation limit, the bright saturation limit of LSST detectors is at 16th magnitude. 16 is something that is towards the faint end for most of our observers. So in that case, again, LSST can provide hints of of interesting stars that perhaps saturate at 16 magnitude, but then they become brighter and brighter for our observers to follow up. So there are lots of opportunities of synergy with LSST that we're going to be talking about over the next 2-3 years in preparation for that wonderful mission to come online. LSST is planned to be online, scheduled to be online 2024, hopefully post-coronavirus era.
Okay, I'm just going through the list of questions and answers, and there is a comment here also about radio telescopes, and you can join SARA, Sarah, and it gives the HTTP www.radioastronomy.org, and there are lots of amateur radio astronomers there that may be interested in supporting some of these variable star projects. That was just a comment. And another question: do you intend to observe RR Lyra stars and perhaps RR Lyra itself? And I'm not sure if that particular star is on our target list, but I think RR Lyras are on our list of stars for particular problems that we can observe. Any comments from anyone on that?
RR Lyras are super interesting stars. If you have objects of interest, please submit a proposal. You can definitely observe RR Lyra with BSM telescopes.
Okay. Next question. What is the cost of one of the BSM telescopes? Well, for us anyway, they're on loan, so they don't cost our network anything because they're on loan from a particular organization in New Mexico. So can't really answer the question then about the cost of those particular reflectors. I don't know, Dave, do you have any comments on that?
We can certainly look up the costs of each of the components. I think for the
telescope itself, we're getting them on loan. We have gotten a lot of equipment on loan, and which is very helpful to us.
But I think to model a one of the BSMs with 180 millimeter astrograph, I would guess you're probably looking at 30 plus K.
I don't know.
That and you really don't need the ME mount. You could use the MYT mount, which would reduce your costs.
Yeah, the amounts we use are pretty expensive, and again, they're on loan to us. Okay, next question. Where can I get advice for setting up my own photometry system? I am new to this, though you used to observe as a youngster. Right now, I have a 5.5 inch, 5.5 Richfield Schmidt Newtonian. I am considering getting a new telescope, perhaps a refractor. So any comments on advice for your photometry system?
I have one. So one of our very newest observing sections is the instrumentation and equipment section. It's still in its infancy, but that is one of the questions that they are aiming to address, is to give basic information on lots of different setups, lots of different things you can do, and sort of the initial, not necessarily costs, but components that you'll need to set up different types of systems. You can also ask on the forums, especially the instrumentation and equipment forum, and you'll get a lot of answers from people who will give you very detailed ideas of what their setups are and more on what you might want to do.
Just to complement what Bert just said, there is a forum for this particular new observing section. So I would like to encourage you to ask there. You will learn a lot about different equipment. Also, on September 5th is when we're going to be discussing instrumentation and equipment. With that observing section is going to be online. So join us for that discussion as well.
Also encourage
Molly
people to start.
also mentioned that Cloudy Nights is a good resource. I'm assuming that's a website.
Yes, Cloudy Nights is a good place for resources. I like that. Yes,
It's a forum.
the forum. Yeah.
I was going to suggest going to star parties, because then you can walk around, you can talk to people. Of course, we're dealing in a pandemic right now. It's not a great idea, but you learn a lot just from hearing what works and what doesn't work, and you actually see what they're using and how they put it together.
Yes, and the other advice would be you have to decide if you're going to develop a photometry system, what are you going to use it for? Are you going to use it primarily to look at stars that vary? Or are you going to use it for supernova? What are you going to use it for? So that will help you determine the types of equipment, cameras, filters, and so on that you want to use. So you have to make a decision early on. What are you going to do with your system? Okay. Another question is magnitude range of stars that can be observed through using the Bright Star Monitor telescopes. I think I said that the range goes from about second magnitude to about 12th, maybe 13th. The signal to noise ratio, the noise in the background gets pretty bad when you get around 13. But the sweet spot is where the best observations are from about magnitude 4 to magnitude 10 visually. Any other comments on that? Okay, next question. What is the magnitude range of a bright star? I think, okay, I just answered that. If I wanted to use my equipment, is there a list of potential objects? I think we don't have like a target list. You may want to come up with your own project, or as Stella mentioned, we have this tool where you can look at stars that the AAVSO has observations on, but has shortage of observations. So you could supplement our observations on that. You want to mention the tool again, Stella?
I was just going to say one thing that we are working on with the observing sections and the observing section leaders is developing some long-term projects with people so that there are areas that you can contribute to right away. We also have alerts and campaigns, which are people asking for data with very specific sort of, I want data on this star over these nights with this cadence. Where you can go if you're curious and you want to help with science or contribute to science in a more immediate sort of fashion.
Okay, any other comments? All right, next question is, can images stored on the FTP server be accessed by VFON?
We addressed that one.
What was that, Stella?
We addressed that one.
Yes, we did. So the answer is yes, it can be. Okay, next is a more technical question. More interested in image scale target, since there is such a large variation from half an inch to 50 millimeters. Okay, I'm not sure I can address that. Any comments on that question? But we're going to put something out on the image scale of the camera for our bright star monitors. I'll answer that question later. Next question. And of course, if I don't answer your question correctly, you can always feel free to send us another comment to elaborate or clarify your question. The next question, will the recording of this webinar be available in the future for streaming? Stella?
Yes.
Okay. Bert?
Yes, it will be. We're going to do some minor edits and we'll post it on our YouTube channel shortly. I'm not sure exactly when, but it won't be too long.
Okay, another question on cameras here. I'm considering purchasing a CMOS camera for this and other work to replace my current CCD. Okay, I guess that's just a comment, and I guess I would agree that you probably should be migrating away from CCD cameras to CMOS. Another question. I'm interested in the dark sky observatory, the large sheds. Would it be possible to get some contact info about that?
I think I can answer that. Preston Starr owns and operates that project. He has an excellent website. He responds to emails. Some of the sites are commercial, some are government. I think a couple AAVSO members besides myself have sites there, have peers rented there. He lives in Fort Worth, so he doesn't live full-time on site, but he is there frequently. And he doesn't want people on site if he's not there, so you have to plan your visits out there to correspond with his. But it certainly he certainly provides an excellent service at a very fair price.
Maybe there's a website or something.
Yes, I mean, you can go to the Dark Sky Observatory, Texas, Google that, and you'll easily find it.
Okay, another question. What is the best way to get started with using the BSM? Are there some suggested targets to begin with? So I guess that goes back to Dave, who's heading up this particular observing section.
Well, currently the proposals are set up as proposer's choice. I found what got me interested in the targets that I used was reading the materials on the AAVSO website. And there's a star of the season. There's discussion of which stars in various categories need more observations. And you need to look at, if the star is within the brightness range that would work. But that's a good place to start.
Yeah, maybe that's something we might think about, is having a list of suggested targets that people could work on. And as Dave has mentioned before, you want to look at variable stars that have a short period. It's better to look at those that have a short period so you can get some interesting observations over your observing time period. So that would be our Lyra stars, maybe some short period Cepheid variables, stars like that. And there could be some eclipsing variables too. Any other comments?
Someone's asking you to say the name of the Texas Observatory site again.
It is the Dark Sky Observatory, LLC, I think, but I always put Texas on the end so you don't get, a lot of other noise that's not what you're looking for. Just Google Dark Sky Observatory, Texas.
Okay, next question. So after the data are taken by the system, we need to make the photometry by ourselves, right? And I guess so what is meant by photometry? If you're looking at taking the observations, raw observations, and turning them into calibrated images, we do that. We will calibrate the images, with the darks and the flats. Now, the actual photometry, that is taking the images that are calibrated and forming a light curve, you can use VFOT to do that, or some other, well, we'd recommend AAVSO software, the VFOT. But there are other ways to do that too. So the photometry that you're talking about would have to occur when you take the observations through VFOT and come up with a light curve or period analysis. Any comments on that? So photometry would do yourselves, yes. So the next question goes back to the cameras again. A lot of interesting comments on that. It sounds like we almost need to have something on your instrumentation group on cameras. Question is, are the data different using CMOS or CCD cameras? And I would address that in saying that as long as you're careful in how you perform calibration, that is, you take your raw image, whether it's from a CMOS or CCD camera, and perform corrections for the dark current and for the flat fielding, I don't think you'll see a major difference. Any comments from anyone else on that? But again, it goes back to how careful are you with your imagery in performing calibration from both the darks and the flats. So it's important to do that. And with the bright star monitors, if weather conditions are good, that is, there are no clouds around at dusk or dawn, we will take sky flats. That's the normal way we take our flats. And so we try to get flats the same night observations are taken. Now, it doesn't always occur, but we try to do that. Okay. Let me go to the next question. As I understand it, your scopes do tracking, but not guiding. What type of variable stars do you recommend observing with them? Have you ever tried exoplanet observing? Well, the first part is not quite correct. We do tracking. As far as guiding, you mean, if you mean a guide star, we don't. However, the ACP software and the other software we use for the imagery, which is, let's see, what is our camera control software? I'm trying to think. Maxim DL. The ACP does a plate solve with every single image that's collected using a Maxim DL. So when it does a plate solve, it will determine if a correction has to be made after that image is taken. So we usually set a error bar for the image uncertainty, and I think it's, for the one I use, is like 2 arc seconds. So if your plate solve gives you if you're off by more than 2 arc seconds, then we will move the telescope back and center it. So we do tracking, but we don't do guiding. However, we can correct using plate solve. What type of variable stars do you recommend observing with them? And I think we said you want to start off, you want to probably look at short period variables, what we would recommend. Have we ever tried exoplanet observing with the bright star monitors? I think we have had a few of the bright exoplanet targets observed with the bright star monitors. I'd have to go back and talk to one of our people who does the target listing, but I think the answer is yes, we have, and we can. Any other comments?
Going back to the issue of guiding versus tracking, just playing with the Texas instrument, the mounts are really very good. And I was able to track a star for 5 minutes, do a 5-minute image without any significant drift, without using a guide scope. So, and it's pretty rare that we would need an exposure more than 5 minutes. In fact, I've never seen one in our system. So I think it adds complexity without adding benefit, at least for the purposes we were using it for. I think if you're doing astrophotography, it's another whole world.
But you're right. I think the targets that we use, generally, I have not seen exposures too much longer than about 2 minutes, 120 seconds. So you don't have much drifting going on. And I think the tracking with our mounts are very, very good. Any other comments on that? Well, there's a comment I got from Gary Walker, because I did send him a question, and he says the CMOS array is 3672 or 3672 by 5496 pixels, and the pixel size is 2.4 microns. And the most sites are binned. That is, by binning, we mean we don't take an image with 1 pixel. We usually bin it. I know we bin 2 by 2 pixels, if that means anything to people as far as binning. And that helps to cut down on the signal to noise and makes the exposures a little shorter also. The binning does help on cutting down the exposure time. That's about it. Okay. Any other comments? And we are getting comments coming in from our people online too about this.
Molly says that binning on CMOS cameras doesn't help a whole lot. You don't quite get the signal to noise ratio benefit you don't on CCD cameras.
Right, you don't get the, but you do get the reduction in the exposure time.
Mm-hmm.
And let's see, another comment.
A question actually that appeared more than once. It has to do with, have you considered problems with the Starlink satellites?
I don't want to get into a political discussion on that one.
Not political, but practically, have you had any problems so far with Starlink?
Well, the way we do our observations is we have someone who does a review of all the images that we take with each of the bright star monitors. That's part of our BSM group, or AAVSO net people. And I would say we get a lot of images that have satellite tracks going through them. Right now, that's not a serious problem. It's only a problem primarily, I guess, with the Starlinks. It would be at dusk and dawn. But the more that go up there, the more problem we will start having with satellite tracks going through our images. I don't know if that answers the question.
I think it just reflects part of your job analyzing data is to look at all your images. And, you know, I'm amazed whether it's an airplane or a lightning bug, or a cosmic ray or a satellite. You just got to pay attention, and you can't just rely on letting the numbers roll through. You got to physically look at the images.
And we do have someone reviewing, as I say, all the images and making comments on whether there's a problem with an image due to trailing, due to satellite going through it, or due to poor focus. So someone is always reviewing that, and so each of the images has a comment next to it if there's a problem. Okay. Let's see, next comment. Are there any plans to have a common queue shared by all sites? That I'm not sure. Dave, I don't know if you're aware of that, or is that something we need to go back to our network people and ask them?
I think it's an interesting idea. I don't think we've done it yet, but it certainly, for example, if you wanted a long time series, could you pick it up from one longitude to another longitude? It's an interesting idea.
Well, that would go to the people who make up the target list. So it might be that you could set the priority of a star to be observed throughout as we go across from the U.S. over to mainland, to Hawaii, to Australia, if it's observable from Australia, and so on. I don't know.
You also have to deal with the logic of ACP and how it's choosing its targets as well. So it's not easy.
Right. And another question on the camera. In regard to hardware, especially cameras, it looks like some of the systems are using ZWO CMOS cameras. Are they the same model cameras? With the exception of, I guess, Dave's site. I think they're all the same camera, aren't they? I believe the answer is yes. I'd have to research that to make sure, but yes. You know, Dave?
Yeah, I believe the answer is yes, too.
Okay, another question on the range of magnitudes that the system is optimized for, and I think I've said that it's visual magnitude 4 down to visual magnitude 10. So we have pretty good signal to noise ratio with those. Any comments on that? Okay, another question. What about setting up another bright star monitor telescope in Russia or Armenia? And I say we'd like to go for that. I think we just need to communicate with Dave and about setting something up. We don't have anything in that particular part of the world. We need to have a wide range of longitudes for the bright star monitors. That would be an interesting concept to have something set up over there. Any comments, Dave?
Well, I'll check with Putin and see what he says.
Well, I think this person is from Russia, so maybe he's willing.
We'd love to talk.
Okay. Let's see, next question. AAVSO, are we thinking in doing any citizen science projects? I think that's separate from BSM. Stella?
We already have online a set of data mining citizen science projects, so individuals can actually use existing data in order to identify properties of stars that exist on VSX right now. I am not sure whether the question pretty much has to do with observing projects, citizen science observing projects. As Bert reminded us earlier today, we have alerts and campaigns that are running continuously. So these are opportunities for citizens to participate in specific projects. These are targets that are being requested by individuals for observations. So these are two ways that citizen scientists can participate in AAVSO projects.
Okay, we're coming up on time limit, I think. I'm not sure what the time limit is, but here's an interesting question I would hope to try to answer. It says, by comparing a given star brightness across the telescope system, and you conduct system-wide calibration. And I know that the developer of the Bright Star monitors, Arnie Hendon, has put in place a number of what are called Landau fields. L-A-N-D-O-L-T, Landau fields. And we try to observe these with all of the Bright Star monitors every night, some sort of these calibration fields. So you could calibrate the fields on all the Bright Star monitors and compare them, how well they're performing. I think that was the intent of Arnie, was to do calibration between the Bright Star monitors using Landau fields. Does anyone else have any comment on that? And Dave, I assume you see that some of these Landau fields are being observed by your Bright Star monitor?
Yeah, they are. And like I said, just as an anecdote, the last project I did using the network, we were also using a 0.7 meter instrument at the Lowell Observatory. And we ended up, the two observatories observing the same target at the same time. And the data was virtually superimposable. So anecdotally, I certainly haven't seen problems, but that's just an anecdote is an anecdote, but certainly the Landau fields provide more consistent confidence building that we're getting the same information from every place.
Yeah, these are fields that have extremely good photometry already done to them. Now, the next question I think might be of interest to
Bill?
you want to comment first, Bert?
No, I was actually just going to raise one question that was asked a couple of times, both in the chat and the Q&A, that I think we should get to because it might have gotten missed in the chat, which was, can the BSM network be used for occultations? I'm assuming of asteroids.
Occultations of asteroids. Well, that's... I used to work in the occultation field. The problem is, if you had video, you could certainly do it. The problem is we have imaging cameras, not video cameras. So you're taking snapshots, and I don't think we have the necessary fidelity to go to short snapshot to capture an occultation. If we could replace one of our cameras with a video camera, then it could be. But I would think occultations are probably not feasible for the Bright Star monitors. Any other comments? If we had video cameras, yes. With our particular imaging system, I think probably not. Here's another question that may be for Stella. Is there a test file that we can use now while trying to learn VFOT?
Question for me?
And, you know, I guess there's a choice course on VFOT, and do you go through a test file that you can use on how to learn to use VFOT?
So as David mentioned, the choice courses in CCD right now that are including VFOT will be using BSM data. So you don't have to have your own telescope in order to learn how to reduce CCD data through VFOT. In that sense, yes, there are going to be test files for VFOT learning. If the question has to do whether we have right now test files for VFOT, not that I know of. However, please contact us if you're interested. I'm pretty sure that there are going to be individuals who can provide data for you to just play around.
Okay, shall we continue on, or we're past our time limit here?
A couple of more minutes.
What's a couple more minutes? Okay.
And then we can wrap. It's up to you, really.
Okay, this will be, by the way, we've had this question a number of times about the webinar and availability, and I think we'll be sending something out so you can find out where it's going to be.
Yeah, it will be posted on the same site with all of the registrations. Once there's a link to the previous webinars, it will show up on that page. Instead of a registration link, there will be a link to the actual video.
Okay, here's one I'll quickly try to answer. Is the equipment ever used for NOVA searches? And the answer to that is no, but if we get an alert about a NOVA and it's fairly bright, you know, within our range, brighter than 12th magnitude or so, it's possible that you could use the bright star monitors to follow the NOVA. I think it's rare that we've done work on NOVAs, but it's certainly possible if a particular user is interested in it. Any comments on that one?
Yeah, I think there is a way to link those notifications through ACP. So, I mean, that is a potential for the future.
But I mean, if a NOVA does occur and there's a particular user who is interested in it, especially a professional, we could probably follow them.
Yep.
Another question, are proposals typically for a series of observations over many days, or would a higher cadence throughout the same night be permitted? For example, to capture an exoplanet transit light curve. That's a good question. I'd have to ask the targeting people, because the cadence usually is, we can do fairly short cadence, but we don't do it over a long period. So, for example, we might do it over 15, 20 minutes. But I haven't seen over a longer time period. Have you, Dave?
I think there are some, but the problem comes the longer the cadence, the less probability the star is going to be favorably positioned, you know, in the sky for the whole run. So if you're doing a several-hour cadence, maybe within an hour and a half, the star is going to be too low in the sky to complete the cadence. So ACP will decide not to do it.
Well, it depends on you know, the declination of the star. That's true. But I think in general, we try to observe as many different targets as we can. So it's a prioritization problem. I guess if we had a new exoplanet that we thought we would be interested in determining the light curve for it, we'd have to examine how we might want to utilize the bright star monitors.
And we can put a maximum priority on a particular project, so it would override all the other projects. But that takes away from somebody else's observing time. But it's certainly doable.
Yeah. Okay. A question here. How the instrumental magnitudes are to be transformed to standard system. Please explain with an example. Well, we usually don't do transformation to standard system straightforward. I guess I'd have to go back. I'm probably not the right person to answer this one. I think we usually do more of just a transformation to a standard system, not using the typical transformation capabilities, but just using some stars that with known magnitudes in the image and transform it to the BVRI or Sloan system. I don't think we go through a standard transformation system that uses all the coefficients if you're talking about that. I'd have to double check on that though. So my answer might not be quite right. Do you have any insight into that, either Bert or Dave?
I think you do that exercise in the photometry class, but it isn't the way you operate on a day-to-day basis.
Yeah, a lot of times we don't do the full transformation. Well, I can check into that. Yeah, go ahead.
Ideally, in order to transform your data, you need to have standard stars of a Landau field of a standard field at the same time or at the same night of your observations. That is the ideal situation. And also, ideally, you need to have photometric conditions, as in the sky would not have variable transparency. Some clouds go in front or some kind of a high clouds, which is even worse, like all these little thin cirrus clouds. You'd also have to have your system well characterized. So again, transformation coefficients. The telescopes are well characterized. So there is some kind of transformation coefficient per telescope. So this standardization of light curves is possible through the BSM telescopes. Also, the telescopes do have Landau fields, but I would like to encourage individuals to also look at the standard stars that have been established in the entire sky by the APAS photometric project. And this way, you will find standard stars within the field of your interesting variable to be able to standardize. Just be careful of the conditions under which the data are taken. They need to be as uniform and as quote unquote perfect as possible, so that you don't have different sky transparency at different parts of your field of view, which actually is possible. I hope this is answering your question. This is a very interesting exercise. It's a very interesting way of presenting the data. And sometimes it's really very necessary to calibrate, standardize your data and calibrate them.
All right.
Hey,
Here's another interesting question, I think, for Stella. Has the AAVSO seen any significant increase in contributions or new membership from us amateur astronomers during these times of pandemic and social isolation?
The AAVSO has seen a constant increase of its membership over the years. So this year is not different than any previous year. So our membership is increasing incrementally, but it is. In terms of contributions, we're very welcoming contributions. We always do. We always need help to support our key programs. We have had some generous contributions by individuals this year. And we're hoping to get more because, well, it's a time of a pandemic. Everybody's sort of struggling with this economy. So with that, I would like to actually invite those of you who are not members yet to consider a membership. Remember, you will get free access to all BSM telescopes and that's for $85 a year. And from there on, we welcome donations, bequests, any kind of contributions to support our program.
Okay.
okay. I think that we should probably wrap things up. Thank you all for showing up to this. It was a really great experience. Thanks to the panelists for donating their time and helping us, put on something like this. I recognize that we still have some questions. Please feel free to ask us individually. You can see Dave's contact information on the BSM page. My contact info is there. You can send messages to aavso@aavso.org or on the forums. We love your questions and we will answer as many as you can ask. But for that, I think we are ready to wrap up.
Yes, and from me, thank you for joining us from all over the world. We wish you a great rest of your day, morning or evening, and we hope to see you in the next several Saturdays where we have other observing sections. We're going to be discussing all kinds of subjects of stellar variability. A special thanks to Dave Cowal and Bill Stein, who have been answering your questions and running this session with us. Have a great rest of your day, everyone, and be safe.
Yes.
So long.
Bye.
Bye.